Hey guys, how's it going? So I figured I would do a quick video without any fancy bells or whistles since I will be taking a break from YouTube shortly. And I wanted to discuss something I believe is very helpful in understanding this whole issue of the horizon and perspective and angular resolution, why things get cut off. And this time I would like to tackle it from another angle, and that is the angular limit of the propagation of light. And we never really discussed this. I never see videos on this, but this is a good example of why obviously you can't see to Europe and why there's a limit to our eyesight and what the horizon actually is. It's not necessarily a cliff, the edge of a ball that you're seeing. There's a very logical explanation for it, and that is simply due to the limit at which light can propagate. And I don't need to go into super detailed explanations to the 10th decimal point of exactly where light will be cut off and all these different variables. All that we have to do is understand some very basic points about light. The fact that light does travel like a wave. You can dispute whether light is a wave or a particle, but regardless, it still acts like a wave and it is still measured in nanometers. We know that the red side of the spectrum is a longer wavelength than the blue side. So we can understand that there is a necessary limit of space through which light can propagate. If it doesn't have enough room, it will bounce off the floor, whatever is around it. If there's not enough room for light to propagate, it is not going to get to the observer. And because of this, the funny thing is, you could take the Hubble telescope, set it on the beach, and you're still not going to be able to see further than about what you could see with your own eye or with a good camera, because there's a limit not just to your eyesight, not just the angular resolution of your eye or the camera or the Hubble Space Telescope, but there's a limit at which light can no longer propagate. So it's not just the receiver, it's the sender, if you want to think of it that way. It's the other side of the connection, the electromagnetic connection. If that side's at too steep of an angle, it can't propagate anyway. So no matter how much angular resolution you have on your side, the viewer side, you're never going to see further than what light is able to propagate. So it's very interesting, and you can look at some crude examples. I have a couple of them here. Now, if we look at a rubber band, we can see that when the angle is great, the rubber band has no trouble resonating. But just like when you're looking out toward the horizon, the angles get tiny and you can no longer see any further because light doesn't propagate further than that. Just like a rubber band doesn't vibrate because it's too close to the table. It's hitting the table, it's diffracting, and there's not enough room for it to propagate, for it to vibrate, oscillate. So you can take the rubber band example. You can also look at a guitar string. And what I did here is lower the action, and this is kind of annoying, but it shows you that when you lower the action, the strings are too close to the frets. So you can maybe hear an open string, but when you start trying to play a note, it doesn't work until you get closer to the actual fretboard or the bridge, and then the angle's a little bit greater, so you can make some noise, but as you can see, when the angle is too tiny, it doesn't make any noise. The note will not play. It's not oscillating properly. And the last crude example I have here for this is a TV. Just check out a TV, go to the edge and try to view it from a sharp angle. It doesn't work. Obviously, the angle plays a big part in how light propagates, how much you can see, whether it's diffracting off itself, it's blurring if it's at too steep of an angle. So it's pretty easily understood that this is an important part of whether light will actually propagate. Now the cool thing is we can view this to scale on a graph. And I love this site because it allows us to put in huge numbers. I've put in Earth diameter and circumference numbers and worked out a bunch of different things, but for this example, and these are in feet. The unit here is feet. So we have 6 feet up here for the observer, the height of the observer. And I put 2 lines. I put a red line, which is the line of sight from the observer to the horizon, which is 15,840 feet, which is 3 miles. And I put another line here at just at 6 foot, and that's just your eye level. And I also put a sine wave in here representing the size of the wavelengths of light, an average of, I think it was 600 nanometers, which is right about in the middle there. And that equals, 0.00002, which is, it's 2 times 10 to the negative 6th is what you'll see on here. So it's pretty cool. And if you zoom out to check this out to scale when you're actually seeing the horizon, I mean, it's ridiculous. Obviously, it just blurs into one line because when you put it to scale, you can see that, it's tiny. Let's look at 1580, which is right about there. And we got to get back to 0. So it is tiny. So what we can do is we can zoom in, and then we can check out how this relates to the wavelength of light. And I think that provides you with a good visual understanding of the fact that at too steep of an angle, light can no longer propagate. And that is why you can't see to Europe. You can only see so much of the ocean, because at too steep of an angle, there's just not enough room. So let me get to 1580 here. So as we zoom in to 15,840, which is where you are seeing the horizon, this is where the line of sight from your eye meets the ocean if you're standing on the shore. So we're zooming way in here, and now you can see we're getting subatomic here. There is the size of a wavelength of light. As you can see, it's 1, 2 up, 1, 2 over. There's the wavelength of light, 2 nanometers. So this is the angle. That's where you're seeing the ocean. Now check out the angle. You can't even see the angle, and we are at a tiny level here. We're zooming into the wavelength of light here. This is 2 nanometers right here. 1, 2. I mean, that's crazy. It's so small. And this just allows you to see that light could never propagate from beyond this point. There is not enough room. It's just ridiculous. So once you understand that, you understand, wow, there is a solid limit beyond which light cannot propagate. And it doesn't matter if it's your eye, the Hubble Space Telescope, the Nikon Coolpix 900, you're never going to see further of the ocean than what light can travel. So you can zoom out a little bit, and then you can see once you get down the line, it will start to fit in there. So, still be refracting off the bottom and the waves are moving, but, at a certain point, you will be able to make out the ocean. You might not be able to make out detail. And just compare this. If you're looking, say, directly in front of you at, say, 10 feet in front of you, you could make out a lot of detail at 10 feet. So if you check out the angle at 10 feet from your eye level, and then look at the, the wavelength of light, it's quite obvious that you can see a lot more detail, because the angle at which the light would be propagating is quite suitable for the size of the wavelengths of light. So look at that detail, no problem. You tilt this up to your eye, you can see quite a bit of detail at the nanometer level. From here, it's going to have no trouble going up to your eye. But then, when you're looking at miles and miles, the angle is so tiny that it stays, there's not enough room forever. You're never going to see that far. It's just impossible. Number one, it's impossible for the light waves to travel to your eye or to make the connection between your eye. Number two, your eye can only resolve about 0.02 of a degree of an angle, which is about the size of a wavelength of light. Funny how they're, interrelated. So like I said, I just wanted to show that, and you can make this number here, gigantic. I don't know, make it 30,000 feet, just to show you that, when you get down to that level, you're never going to be able to see that far. That the light just stays tiny forever. The space that would be under that wavelength would be so tiny, you're never going to be able to, obviously light will not be able to travel to your eye, will not be able to make the connection. So yeah, like I said, I just wanted to really explain that there are limits to not only what you can see, but limits at which light can propagate. I mean, it just doesn't propagate beyond a certain limit. So another way to visualize this is that when you understand there is a vanishing point and how your eye perceives light, it flips the image, there's an inflection point, which is your eye level. This eye level is an inflection point. So everything that you can see below your eye level hits an inflection point. And guess what? That inflection point is the horizon. That's where everything that you can see above your eye level, when this angle here gets so tiny, that's where the vanishing point is. And this is what it's displaying in your eye. It's displaying the sky until the angles get so tiny, and all this stuff is going to blur. You're not going to see as much, obviously, toward the horizon because the distances are so great. And then below your eye level is the same thing. It renders everything below your eye level, and then it will eventually hit this inflection point, and that is the point at which the slope, or this light here, you see this line as you're scanning everything below. You're not really scanning, but these connections are being made to your eye of whatever light is, whatever you think the nature of light is. It's pretty obvious that this is how it comes into your eye, just the way it comes into a camera. Hits the horizontal inflection point, which is the horizon, and then starts to render everything above your eye at your angular resolution limit in your eye, obviously, which is why you have that 0.02 degree of a tick downward, which just so happens to equal about the area that light can get to your eye anyways. So this, I don't know how you can really argue with this information. Even if you think you live on a ball, the fact is this is how light comes into your eye. These angles play a part on how much you can see, what you can see, how much detail you can see, and also how far light can travel. And amplitude of light, I didn't even discuss that, but that also plays a part on how far light can travel, whether it can vibrate all the way to the source or from the source to the viewer. So we just need to know that there are fixed limits on these principles of light, these properties of light. So it's very interesting, I think. And like I said, it doesn't necessarily mean that you live on a ball just because there is a horizon. I mean, you have to admit, even if you live on a ball, you know the horizon is a product of your eyes. It has to be. And the other fact is that it's always level. It's always horizontal. You can argue, oh, we live on a ball and there's curves somewhere. We go high and we see a curve. But the point is, it's always horizontal. It's always perfectly level. If you lived on a ball, there would have to be examples of horizons that were not perfectly level. You can say they're curved or straight or whatever, but there should be horizons where one half of the horizon slopes down, or say it's tilted. There should be horizons that are tilted like that. Check that out. Why are there no horizons like that? Like a golf ball. I mean, the Earth cannot be a perfect sphere. I mean, it would have to be so perfect for the horizon to always be perfectly horizontal. The only reason the horizon is horizontal all the time, it's level, is because that's your eye. That's how light enters your eye, and your eye is stabilized to gravity, or to whatever you think gravity is. It's a vertical force, and your eye stabilizes to that to make the perfectly horizontal horizon in your eye. That's why it never changes. You can tilt your head, the horizon doesn't change. And like I said, funny enough, you never find a horizon. If it's a physical horizon, if it's a cliff or a ball, whatever you think it is, there would have to be examples of horizons that are not perfectly level. There's no way the Earth, this gigantic Earth, is so perfectly level. Even a golf ball has dimples. You would have to have examples of horizons that are not perfectly level. They would be, curved or tilted, and there would be half level and half tilted horizons. So it just doesn't even make sense. I don't even how you can believe you live on a ball I can understand the programming, but once you are presented with the information, you have to think about it and understand there's no way we're living on a perfect sphere that would never have any curved horizons or tilted horizons. And again, once you understand how eyesight works and how there is I call it the inflection point. There's a point at which the the light waves travel into the eye, and then there will be a horizontal point, an inflection point. That slope of these light waves goes from negative to positive or positive to negative. And that inflection point is the horizon. And the vestibular ocular reflex in your eye maintains that perfectly horizontal in relation to gravity, that straight up and down force that we have, whether it's electromagnetic, electrostatic, whether it's some magical tractor beam. I just think it's interesting. I think it's fascinating. I'm amazed by it. So I just figured I would at least share some more logic and my understanding of it. And, hopefully it at least helps one person. Yeah, so that's about it. Like I said, I will be taking a break from YouTube. I don't know if I will be back. Thank you so much for watching. I hope this wasn't too much rambling. I don't do too many videos like this just for that reason. But anyways, thank you so much, and peace out and adios.
Going nowhere, going nowhere, going nowhere. I get up just to go to bed. Check to see that I'm not dead. I stay up until the dawn. Bishop takes my pawn.